Today we're going to be doing lessons 10.3 and 10.4. This is the last lecture of the semester, and we're going to begin with 10.3, learning about hyperbolas. A hyperbola is similar to both a parabola and an ellipse, where if this were an xy coordinate system, a hyperbola looks kind of like this shape right here. You could look at it as an ellipse that's been cut down the middle and the two sides were flipped. You could see it as two different parabolas, whatever. This hyperbola also has a focus. Let me draw this a bit better. The focus is going to be directly, it's going to be on this axis directly in front of the vertex of one branch of the hyperbola, and it's going to determine how the hyperbola opens. The two branches, by the way, this is called a branch. The two lines are both called branches. The two branches are identical to one another. Even though they look kind of different in my drawing, they look like they're different distances away from the center, they ought to be identical. And they have two focus points that are also going to be an equal distance away from the center from one another. Through these two foci, we are going to have something called the transverse axis pass through. The transverse axis, in this case, is the x-axis, but it's just a straight line that connects the two. And then where the transverse axis crosses the branch, that is our vertex. And then we also have a center, which is supposed to be the y-axis. It's more like over here. But if this were drawn precisely, the center would be at the y-axis because this is a parabola at origin. We have two different equations that we'll use to define hyperbolas. We have an equation for a horizontal transverse axis, which is pictured here. It's going to be x squared over a squared minus y squared over b squared. It's going to equal 1. You might notice this equation is familiar rather. It's very similar to the equation for an ellipse. In fact, if we were to make this a plus sign, we have an ellipse equation. But the subtraction, the minus sign, tells us that this is a hyperbola. And this is a hyperbola that opens horizontally. We also have parabolas that open vertically. It would look something like this here, with this, the transverse axis, being a vertical line. And the equation for a vertical hyperbola is going to lead with the y squared over a squared. A is always out front, minus x squared over b squared, and that's going to equal 1 as well. The a and b give you information on the vertices, so I'm going to erase these poor drawings, and I'm going to draw a coordinate system. So if we had an xy coordinate system here, and we are given a hyperbola equation, let's say we're given a hyperbola or a horizontal hyperbola equation, we are going to have the center at origin, and the distance to our vertex is going to be a, the constant a. So this distance here is going to be our a value, and then the b value is going to be this one right here. This a value can be, well, the a value also represents this distance. This is also a. The b value also represents this distance. These from B to the center to B, these are the same. And you can draw a rectangle on these points. So the rectangle is going to look kind of like this. And now we can actually shape our hyperbolas. So since this is a horizontal equation, we know like this is the transverse axis, and it's going to open this way. But to determine how they open, we are going to draw a line through the corners of our box. So let's have a line go from here to here, and then another line from here to here, roughly. These lines are going to intersect at the middle, and they are going to become asymptotes for our hyperbola. So the hyperbola branches are going to begin at the vertex, and they're going to go out and get ever closer to the asymptotes without touching them. And that is how we sketch a hyperbola. We can do the same thing with a vertical hyperbola. We would just, with a vertical hyperbola, I'll draw a small version. Our a value becomes this, this value right here, the vertical value. Our b value becomes this value here. And we would draw another rectangle. And I'm going to try to do a quick job. The hyperbola based on this vertical, there we go. I'm running out of room to draw here. I can't draw below this. Is going to open upwards. Do a quick example with some real numbers. If we were given the equation x squared over 9 minus y squared over 16 is equal to 1, what we can determine based on what we're given is that this is a hyperbola because we have a negative sign, and we can determine that it opens horizontally because the x term is leading. That means our a term is the square root of 9, our a term is 3, and our b term is the square root of 16, which is 4. And we can draw this. We're going to have a lot of rough drawings in this lecture, and I apologize. Since it's horizontal, the A is going to be along the transverse axis, the horizontal axis. Let's just say this is 3 units, and we have an equal 3 units over here. The B is going to be 4 units up. That's roughly here, and we have an equal distance here. Now we can draw a rectangle connecting these dots. And once we draw that rectangle, we are going to draw our asymptotes that contact the corners of our box. That's hard to draw this line. And we'll draw that. And now we'll draw the branches of our hyperbola. It's going to begin at the vertex and open, getting closer to the asymptote, but not touching it. And this is a graph, a rough graph of x squared over 9 minus y squared over 16 is equal to 1. Now, if we were to flip this, if we were to have If we had y squared over 9 minus x squared over 16 is equal to 1, that tells us that the hyperbola opens vertically, and our a value, let's do this, our a value is now going to be the vertical value. It's this value in front. That is 3, so we're going to count 1, 2, 3 up and 3 down. Our b value is now the horizontal value. We're going to count 4 over and 4 over on the other side, and we'll draw this box. We'll draw asymptotes based on this box. I'm going to try to do this quickly. That's sort of correct. And then the hyperbola is going to open from the vertex towards those asymptotes like this. And I don't really have room to draw it very well on the bottom. We could also be given a more standard form of a hyperbola equation. We may have 4y squared minus x squared is equal to 16. Or maybe we were just given this equation and told to graph it, and we don't know if it's going to be a parabola, hyperbola, whatever. What could tip us off is that we have subtracted variables that are squared. So that might tip us off that this is a hyperbola graph. And we'll begin by making it look like the general form equation that we're familiar with. So we're going to do that by making this constant over here equal to 1. To do that, we'll divide both sides by 16. That's going to give us 4y squared over 16 minus x squared over 16 is equal to 1. Simplifying, we can say that y squared is over 4 minus x squared over 16 is equal to 1. And now we can figure out things about this hyperbola. We can tell that it's going to open vertically because the y variable is leading, and we know that our a value is going to be this the square root of this 4, that's 2. And our b value is going to be the square root of 16, and that is 4. And we can sketch this. I'm going to make a graph. Our hyperbola opens vertically, so our a value is going to be on this vertical axis. We're going to count up 2 units and make a mark for one of our vertexes. We're going to make another vertex down here. Our b value, the b values are on the horizontal axis, so we're going to count 1, 2, 3, 4, make this mark here. 1, 2, 3, 4, make this mark over here. And we're going to draw the rectangle that connects these dots. And I'm going to try my hardest to draw this line. Dang, okay. There. I'm trying to draw at least one neat drawing for you. That's pretty close. And when we draw our hyperbola, we're going to begin from the vertex, open towards the asymptotes, but never quite touch them. Like this. In a problem like this, we could be asked to generate equations for the asymptotes of our hyperbolas. Remember that these hyperbolas are straight lines, and remember that the straight line equation is y equals mx plus b. where m is the slope, rise over run, and b is the y-intercept. These particular asymptotes go through origin. That means the y-intercept b is 0. So we're left with just y is equal to mx, meaning, well, and we know that the slope is rise over run. In this particular problem, we have a rise of a and a run of b. So if our slope is rise over run, our equation is going to be, for this line, the rise, a, over the run, b, times x. So this is for this line right here. And if we wanted to make an equation for this line, it's a similar process. It's going to be the rise over the run. However, we are going down. This line goes downward, meaning our elevation is dropping. Our rise is actually falling as we increase in b. So our a is negative, making the whole thing negative. So the equations for these asymptotes for a vertical hyperbola is going to be y equals a over bx and y equals negative a over bx. Now, if this were a horizontal hyperbola, remember the b value is going to be, that's a small eraser, the b value is going to go here, and the a value goes down here. So if this hyperbola were horizontal like this, our equations for the asymptotes are going to change. The rise is now going to be b, so we're going to have y is equal to b over a x, and y equals negative b over a x. And we would just plug the a and b that we get from this problem into our new asymptote equations. So for the original problem that we did, y squared over 4 minus x squared over 16 is equal to 1, our equations would be 2 over 4x and negative 2 over 4x. And these would both simplify to 1/2. You might be given information about the hyperbola and then asked to generate an equation that represents it. So if we are told that a hyperbola has vertices of 0, x, and positive and negative 3y, and has asymptotes with equation y equals positive or negative 3x, we can generate an equation for that. Now, we've combined the asymptote equations into one by writing positive or negative. The way we would find it is we want to determine if it's a horizontal or vertical hyperbola. So we can try to quickly graph just to help us visualize it. If the vertices are at x equals 0, y equals positive or negative 3, one vertex is going to be here, the other vertex is going to be here. That means these hyperbolas are going to be opening this way, making this a vertical hyperbola, meaning y is our leading term. This y squared is our leading term. And our vertice, our a, is going to be the distance from the center to the vertice. This is a right here. That means a is 3. We're going to write 3 squared. Now we don't know our b term yet, but we do know that x squared is our second term, or the numerator of our second term, and we know that we can find our b term with our asymptote equation information. So if we were to rewrite this as a over b, that's going to give us positive or negative a over bx. A is 3, so we can write positive or negative 3 over 1, x is equal to positive or negative 3 over bx. And in this example, it's easy to see that for these two things to be equivalent, b has to be 1. So our b value is going to be 1 squared. It's going to equal to 1, and we can clean up this equation by writing y squared over 9 plus x squared over 1 is equal to 1. We can also generate an equation for a hyperbola given the vertices and a point that the hyperbola passes through. So to begin, let's determine what direction our hyperbola opens into. And we can either just look at this and see our vertices lie along the horizontal x-axis, so it's going to be a horizontal hyperbola. We could also go ahead and graph it, just draw it quickly to some extent if we have trouble visualizing it just by looking at this coordinate system. We'll plot the points. Our vertices are at positive and negative 2, 0, so that means there's a vertex here and here. And that means our hyperbola is going to open this way. Well, it's going to cross through the point this way, and it's going to go this way. So that means our leading term is going to be the x squared term. So we can go ahead and build what we know. We're going to have x squared over some a. Recall that a is this distance right here from the vertice to the center point. That is 2, so we're going to have 2 squared here. And we're going to have an unknown b. And we don't know how to find that b immediately. We don't have equations for the asymptotes, but we are given a point that one of these hyperbolas, or one of the branches of the hyperbola, passes through. And that is positive 3, positive square root of 3. So we can plug that point into our equation to solve for b. So let's do that. When we plug 3 in for x, 3 squared is 9. We're going to have 9 over 4. When we plug square root of 3 in for y, square root of 3 squared is 3. It's going to be over b squared and set that equal to 1. Something we can do to quickly make this, having our variable in the denominator, it's kind of annoying to work with, but if we take the product of this denominator and this denominator and multiply the whole equation by that, it's going to make our process simpler. So we're going to multiply the entire equation by 4b squared. So when we multiply 9/4 by 4b squared, I'll write it out fully. Subtracting 4b squared times 3 over b squared, and setting that equal to 4b squared. Our b squared cancels here and here, and the 4 cancels here and here, and that leaves us with 9b squared minus 12 is equal to 4b squared. We can simplify this a little bit further. We'll subtract 4b squared from both sides, add 12 to both sides. That's going to give us 5b squared is equal to 12. B squared is equal to 12 over 5. And then we can plug that in to our equation. So instead of solving for just b, we have b squared, we want b squared, so we'll put that in. That means our final equation is x squared over 4 minus y squared over 12 over 5 is equal to 1. What about hyperbolas that are not centered at origin? You might guess how we do that, so I'm just going to write our standard equations for a hyperbola at origin. For a horizontal transverse axis, we have x squared over a squared minus y squared over b squared is equal to 1. And for a vertical transverse axis, we have basically the opposite. And our principles for moving the center point of our hyperbola, or the center point of our shape, whatever it is, are going to be the same. So when we modify y before the squaring operation, we're going to move it up or down. When we modify x before the squaring operation, we're going to move it left or right. So if we wanted the general form of a hyperbola whose center was at 3, 2. So over here, we have our graph. Our hyperbola is at x3, y2. It's going to look kind of like that-ish. We would use our horizontal equation here, and we would write x minus 3 squared over a squared minus y minus 2 squared over b squared is equal to 1. We can do the same thing for the vertical hyperbola. Remember that the h always goes with the x term and the k always goes with the y term. So if we wanted to do a vertical hyperbola with center 3, 2, we would still have y minus 2, because the k always goes with the y term, over a squared minus x minus 3 squared over b squared is equal to 1. Let's take a expanded standard form of an equation. 9x squared minus y squared minus 36x minus 6y plus 18 equals 0. And let's convert this into the standard form of a hyperbola equation, or the general form. I can't remember, honestly. First, if we were just given this and told turn it into the standard form of a shape, and we needed to determine what shape it was, we could see that our x squared term is we have a y squared term being subtracted from an x squared term. That tips us off that this is a hyperbola. And we're going to approach this the same way that we approached transforming other equations. We're going to combine our like terms, or I guess consolidate our x terms and y terms. So in doing that, let's put the 9x squared together with the negative 36x, and now we'll put together the negative y squared minus 6y. And let's move the constant 18 over to the other side, negative 18 over there. Now we can use completing the square to turn these into quantities squared. I can't remember the exact term for it at the moment. To do that, let's we want the coefficients in front of x squared and y squared to be 1, positive 1, to make our completing the square easier on us. So we're going to take a 9 out of this x squared quantity. And when we divide 36x by 9, we get 4x. We're going to leave a space here to make completing the square easier. And now we're going to make the coefficient of the y squared term positive 1, which means we pull that negative sign out to the front, and this is going to become y squared plus 6y. That's an easy mistake to make, is missing that we are turning this y coefficient into positive 1. So be cautious of that. And we're going to leave some space. And we will set this equal to negative 18. Now we're going to start the process of completing the square. We are going to add in half of the coefficient of our x term. That is negative 2, and that's going to be squared. Over here, we're going to add in half of the coefficient of our y term. That's going to be a positive 3, and that's squared. Now we need to make this equation equal on both sides. So negative 2 squared is 4. 4 times 9 is 36. I shouldn't use a calculator. Yeah, it's 36. So if we're adding 36 to this side of the equation, we need to add 36 to this side. And now if we are, let's see what we're doing to this. We're adding in a 3 and we're squaring it, so that's 9. However, this quantity has a coefficient of negative 1. So that means we need to subtract 9 from this side of the equation. Now we can turn these into quantities squared. This is going to be 9 multiplied by x minus 2 squared. And we're subtracting the quantity y plus 3 squared. And that's going to be equal to 9, I believe. 30, yeah. It's going to be equal to 9. It's 36 minus 18 minus 9. The final step is making the constant side of our equation equal to 1. To do that, we're going to divide everything by 9. So the 9 over here is going to cancel. That's going to leave us with x minus 2 squared over 1, subtracted by, minus y plus 3 squared over 9 is equal to 1. And we can leave it in this form. You can write this as 3 squared, it doesn't matter. That is taking this standard form and converting it into a general form. We're going to end today's lecture with 10.4, and that is solving for nonlinear equations. We've done solving linear equations before. That's where we had two lines, the equation for the graph of two different lines, and at one point they intersected. And we wanted to find the coordinate point that they intersected at. That was called solving a system of equations. We can do that with nonlinear equations as well. So let's take y equals x squared minus x minus 1. You might recognize this as a parabola. And let's have just a line, 3x minus y is equal to 4. We want to find where these two graphs intersect. The method we're going to use is we're going to solve for a variable for one equation, then we're going to plug into another. So we already have y solved for in this first equation here. So we're going to plug this solution for y into this equation down here. When we do that, we're going to have 3x minus a quantity, x squared minus x minus 1. That's equal to 4. We'll distribute this negative sign through. That's going to give us 3x minus x squared plus x plus 1 is equal to 4. And now we can start combining terms. While combining terms, we also want to put this to solve for x. We need this to be a trinomial that equals 0, right? That's how we are going to use either factoring or the quadratic formula to get a solution. So we want the coefficient of the x squared term to be 1. We're going to add the x squared term to the other side of the equation. We will combine the x terms and also move it to the other side of the equation. So 3x plus x is going to be 4x. Move to the other side is negative 4x. And now we'll subtract 1 to give us plus 3. And that's going to be equal to 0. We can use any method we want to solve for x. Factoring method's pretty easy in this case, so we're going to use factoring method. This is going to be x minus 3 quantity multiplied by the quantity x minus 1 equals 0, meaning our solutions are x equals 3 and 1. Now we can take these solutions for x and put them back into the to this problem right here, or I guess either of them, and we can get solutions for y as well. But we need to distinguish the two. And what that means is we're going to write for x equals 3. And now we can plug x equals 3 into this equation here. So for x equals 3, y is going to equal 3 squared minus 3 minus 1. 3 squared is 9, minus 3 is 6, minus 1 is 5. So when x is 3, y is 5. We'll do the same thing for 1. For x equals 1, y is going to equal 1 squared minus 1 minus 1. This is negative 1. So when x is 1, y is negative 1. We can rewrite this in ordered pair format, giving us the 2 points where these two graphs intersect. So when x is 3, y is 5. And when x is 1, y is negative 1. This is how we can record our solutions. And if we were to go into a graphing calculator and graph these two, we would find that the parabola and the line intersect at these 2 points. Or if we were to even hand graph these, these are where the lines intersect. More complicated equations might give us 4 ordered pair solutions. But the process of solving is the same. You could even use the other method that you learned earlier in the semester where you put the two equations on top of each other and you either add or subtract. I can't remember because I didn't teach that, and I haven't actually personally used that. I didn't learn that when I was in school. You can use that to solve for x and y as well. One thing is, if you ever get an imaginary solution, let's say one of your solutions for y is the square root of a negative number, that just means that that intersection doesn't exist. The graphs don't actually intersect at any point. That is all for 10.4, and that's actually all for the semester. We have a couple more tests coming. Maybe 2. I'll have to make them and figure it out. But the homework for this week is going to be the even problems. Let's write it down. It's going to be 10.3, evens through 24, and 10.4, evens through 28. And a test might be sent out with this lecture as well. I think we need to do test 9 or maybe even 8. I think it's test 9. I'll figure that out, and you'll receive it in the same email. Have a good week.